on, I think it was Tuesday, I was talking to circuits and electronics and circuits, and sitting there and telling them about how like my mom abandoned me because I really enjoyed flip-flops or something.
I was the own president of Buffett.
Yeah.
Are you applying?
Oh, I wish. I could do a better job. But the thing is, in academic circles, you don't overstep your bounds. So like you don't have the junior engineer apply for a vice president or a president role at a company.
Yeah.
It's just, unfortunately, that's the nature of it. You have to have more success behind you before they want to hire you.
I dressed myself this morning, is that good enough?
Doesn't matter.
So what you're saying is I shouldn't try to do that?
If you become our new president, like, I'll have to take back all those mean things I said to you. Yeah, this is where things come back to bite me. All right, what we're going to talk about today is timers. Okay. Whoa. I wrote that on the board and it doesn't even show up at all. Grabbing a black marker. All right. Are you sure you don't want me to go represent Josh?
No.
I mean, I've never punched anyone other than my brother, but I'm pretty sure I could survive.
Hey, you're still recording now.
The last one standing.
I'm doing this for you, Josh. Okay. So we are talking about timers today. Now, timers are wow. Hold on.
Timer's wow.
Is it the glare?
Yeah, it's the lights that are just like right there. I'm gonna see if. Hold on, I got this. I got this. Because that also helped.
I'm gonna click it once more.
No, that'll be good. I think we'll be okay. Thank you for that. So timers are kind of an underrated cycle in this. Well, they're an underrated component, really. Timers are used in just about everything that an electronic circuit does. Okay? Why are timers so critical? Anybody know? Why do they matter so much? What's so great about timers?
They send an electrical signal at a known value. Or a known time.
They do. Yes. Yes.
They're binary.
Well, they are binary, yes. If you've already done the reading assignment, like they go up to like 64-bit, which is still like really not a lot of time, but why are they so important? Well, one of the things that they do, and this is only one of the features, is what timers are responsible for is really for measuring not just how much time has elapsed, but also how many different bits have been sent. Okay? It almost acts like a bit counter. Because when you have your oscillator is producing signals that go like this. Your system usually only reacts on either the positive or negative edge. And the reason for that is because you don't want the system to be able to be changed while the clock signal is on, or else you kind of endanger your whole system, because if it turns on, it stays on, and then things start shifting. By the time it shuts off, you know, everything at the beginning is different from everything at the end. And that does, that does cause problems, because you can erase memory, you can accidentally lose memory that way. So it only goes, it's a positive edge triggered system. And what a timer does is it counts how much time has passed between this edge and this edge, how much time between this one and that one. And what that does is it tells you how many bits have been transferred in that time. And you can use it to find how many bits have been transferred. Because if you know what your oscillator speed is and you know how much time you've taken, it's just a simple division. So if you're sending a 16-bit signal back to back with another 16-bit signal, the system itself has to be able to say, okay, this is one word, this is another word. That's basically like the timer is what puts the space in between those words, if we're doing the analogy of like typing words. Is it'll say, okay, it's been 16 bits, move on to the next one. So that is one application for timers. Timers are critical in the system because they help regulate system information. It gives the system enough information to say, you've had enough, move on, next one, next word, next process. A lot of the registers are dependent on the timer cycle, because if it collects one word and then the registers will empty that word into memory or into something else, or will be cleared actually when the timer reaches a certain value. Timers also have other features aside from just simply counting the number of bits that have passed, the number of clock cycles that have occurred. Timers are also very important for determining whether or not the system is still working. And this is called a watchdog timer. Bless you. And here the idea is if your clocking cycle is changing and your registers are not moving, your watchdog timer is going to say there's a problem. And because it recognizes it as a problem, it'll just wipe the registers clean and say, all right, let's keep going. And it has to do that because, quite frankly, the electronic systems are so volatile that if you lose a single bit in communication, it doesn't happen very often. But I mean, if you lose one bit in every 100 million cycles, you're going to run into an issue where 100 million cycles, if you're running off of a 2.4 gigahertz system, well, 2.4 gigahertz means you're operating on 2.4 million cycles per 1 second, which means you're losing a single bit every about, every 50 milliseconds. Now this is obviously our computer systems are more reliable than this, thankfully. But I mean, this is a pretty grave error. We have to be this accurate in electronics, because as soon as you lose one bit, you now have a word that doesn't make any sense. And as soon as that happens, your registers do not know how to empty properly, and they're just kind of stuck. And the watchdog's timer's job is to look at this and say, well, the registers aren't empty because they're full of trash that don't make any sense anymore because our data got corrupted. We need to stop, start, go back again, do this again. Okay, so that's kind of the purpose of a watchdog timer, is to watch for errors in the system and watch to make sure that the system is continuing to operate even if errors are present. So yeah, it gives a little bit of gravity to this, to think that one little mistake in 100 million can happen once every 50 milliseconds, 20 times a second. Kind of crazy, but yeah, we do have, I mean, our electronic systems are more reliable than that, thankfully, which is why we are able to do so much without having to go back and reset all of our electronic systems. Okay, so there's another critical feature of a timer. Another feature that a timer is used to do is timers are used to build PWMs. Now, we've talked a lot about PWMs in our classes because, quite frankly, I love them probably more than I should. PWMs they're not that complex, but it's the timer's job to say, okay, on for this long, off for this long, on for this long, off for that long. And it becomes a customizable timer. And that by itself, I mean, it's a PWM signal, but it has to run through a timer. And the timer is the one that has to control it. And the accuracy of the duty cycle here is critical. Because if that duty cycle changes by 10%, I mean, that's not a huge time difference here, but you're going to see a dramatic change in the power output of whatever system that's connected to, or whatever light that's connected to, or motor, or whatever it is. So having a very accurate timer is critical for PWM signals. And there's a lot more applications that the book brings up as far as where timers are used, how timers are worked with. But one of the fundamental concepts of a timer is that a timer the job of the timer is to count oscillator cycles. Okay? Oftentimes the timer itself, I mean, the timer doesn't just sit there and be like, well, according to the world clock, exactly 53 seconds has passed. That's not how it works. A lot of our systems, that's how I like to think personally. I like to go to the world clock and be like, world clock says this. But in reality, the timer actually is based on oscillator cycles. Oscillators could also, well, oscillators probably could be argued as one of the most critical components in a system as well, between timers and oscillators. But that's because an oscillator's job is to produce this positive edge whereby everything changes on the positive edge. By the way, if you ever come up with a system that does not require a positive edge to change, you could increase your processing speed dramatically. Right now, a lot of high-end processors can go up to like 2.4 gigahertz. That's pretty common in today's computing. There are oscillators that can go higher. They're much more expensive. But 2.4 gigahertz, that is right now the limitations on our computing. If we could get them to go to 2.4 terahertz, our computer systems would be 1,000 times faster. So just by being able to increase the speed. Now, there are also some other issues that are unrelated to the oscillator. A lot of components have finite switching times, where you'll have a component that takes maybe a nanosecond to shift states. And if your oscillator is operating at 2.4 terahertz, then you're having a signal, well, okay, let's say you have an oscillator operating at 1 terahertz. The tera is right above the giga. 1 gigahertz processing speed means that every cycle is occurring every 1 nanosecond. Okay? If you have a switching speed of 1 nanosecond, this actually works fairly nice because it means every oscillating cycle, you have the ability for whatever that thing is to switch within that time. Okay, so the computer hardware that we have has to have a, well, as it stands right now with a 2.4 gigahertz system, it has to have a switching time of less than 1 nanosecond. But if we were to operate off of 1 terahertz, this is now 1 picosecond. It's 1,000 times faster. Your electronic components have to have the ability to switch in 1 picosecond. Everything takes a finite amount of time to operate. Electricity travels at the speed of light. What is the speed of light? Anybody know off the top of their head? You just walk around with these numbers? My brother does. We'll look it up real quick.
First one to get on Google Lens.
Hey guys.
299,792,458 millimeters a second.
So it's about 300 million meters per second. Okay, 300 million meters per second. If you had to travel 1 meter and you have 2.4 gigahertz clocking cycle, how fast does that clocking cycle go 1 meter? Okay, so 2.4 gigahertz clocking cycle over 1 meter. How would we figure out how long it takes for that signal to go 1 meter? Well, quite frankly, this doesn't matter. This is the only thing that does matter. If we divide this by this, we'll get a 1 per second. If we divide this by this, we'll get the number of seconds. So if you divide 1 meter by 300 million, calculator time. Okay, which is 3.3 nanoseconds. It takes 3.3 nanoseconds for an electron to travel 1 meter. Okay, and that is a physical limitation that we have. A lot of PCBs and circuit boards, they have to be very small. You don't have something communicating with the other sides of the room because, quite frankly, we have this physical limitation. Communication can only happen traveling 1 meter per 3.3 nanoseconds. So this is another thing that we're fighting against. If we're going to have a clocking speed where we have to have a definite on-off time, if we were going to try to make this any faster, it takes 3.3 nanoseconds to go a meter. Well, if you want this to go a millimeter, a single millimeter, that takes 3.3 picoseconds. If we have a clocking speed of 1 terahertz, what we're now looking at is our clock oscillates 3 times before this signal moves 1 millimeter. which means that your system is going to become dependent on where the components are. If you want to talk about limitations in electronics, we are very quickly reaching a cap to what we can do with our electronic systems. Not because our oscillators need to be better. We have better oscillators. They're more expensive, but we have better. But because all of a sudden it messes up our system communication. If I have 3 components over here separated by maybe 15 millimeters, okay, 15 millimeters apart. So this is 15 millimeters. If I send a single signal that branches out and goes to all 3 of them, this may be operating at a slightly faster speed than the others. This may be receiving that information. So if this is transmitting back, this, whatever hub this is going to receive this information prior to this information. They'll be off. Which means now you don't just have to code to make sure that your system works, which is what we have to do now. You also have to time your circuits systems so that they transfer information at the same time. You may have to cause this to pause for a few nanoseconds or picoseconds so that these components can catch up, just because there are millimeters differences between them. This is not the kind of issues that any electrical engineer wants to fight, but this is what the generation of looking towards where we're going, this is where we have to focus. We don't have an endless world of possibilities just by continuing to improve on technology. We have nearly reached our maximum speed for computation, which is why many scientists, brilliant computer scientists, are not going towards let's build faster oscillators, but they're going towards let's build quantum computing mechanisms. Because now it's, well, we can operate it at the same speed, but we can transfer more data in one system setting. Okay? Does that make sense? So timers are critical, and if we were to make them any faster, they would have to become more critical. In systems where we're communicating across meters, now, where we're communicating across a single meter, this now does become important. Because your clocking speed of 2.4 gigahertz, 2.4 gigahertz, let me see if I can do head math. What's 1 divided by 2.4? It's like 0.4 something. So you have a clocking change every 0.4 seconds. Okay, it takes 3.3 nanoseconds to go 1 meter. That means your system is going to be off. And it's unavoidable. We can't make light travel any faster. Although if we could, we'd figure out a way, because that'd be awesome. Okay, so timers are critical even in these components to make sure that data lines up. Because if data doesn't line up, it doesn't mean anything. It's like the guy who doesn't respond to a question until like 15 minutes later in class. So does anybody know what is a microprocessor? No? Okay. Let's talk about cheese. So cheese is delicious. Microprocessors are fun! Okay. That guy. That's the idea though. You have to have the timing be consistent. And this is one of the most critical features of the timers, are that they force things to be all on the same timing circuit. All right, any questions about this? Okay, next week, Monday, we're gonna get started on programming the Arduinos for your project. I need all of your Gerber files. You guys handed in a Gerber file? I needed the zip folder. I will need a zip folder. Huh?
I thought I gave one.
One of you just, I don't know, we talked about just uploading the file, and then I tried to see if that worked. It did not work.
Yeah, I re-uploaded
Okay,
a zip folder.
okay. Does everybody have their zip folders handed in then?
That's doing mine.
I did it to the same assignment.
Yeah, I helped make yours, so I should have yours.
What's their lead time? How long will it take to get everything out?
They say about a week. So I'll try to order them this afternoon, if that's the case. And then we can move forward with programming it and then plug it all in the week before finals. That's my hope.
So program before it's in the.
Yeah, just because we can, and we can do that step while we're waiting. Okay, any other questions?
What's the theory of kind of like quantum computing? How is it so much faster?
Okay. That is a great question. I love this question because I think it's fascinating. The thing with the quantum computing is right now, everything that we have is streamed into a binary system. Okay, so if I want to represent the number 1064, I have to do so by saying, hold on, we got 256, that's, I believe, no, start with 64, that's 2 to the 6th, 128, 256, that's 2 to the 8th, 512, 1024, it's 2 to the 10th. So this is This is 1, 0, 0, 0, 0. And then we have a 2 to the 5th. And then we have a 2 to the 3rd. Okay, so we represent the number 1064 as a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 digit number. Actually 11 digits, I need to move. There's one more 0 in here. It's an 11 digit number, okay? And the issue with doing that is now we've taken 4 digits and expanded them into 11. And that means by comparing the difference between these two, it takes almost 3 times longer to transmit a signal in a binary system as it would to do it in a decimal system. If we could deal in decimal systems, we could send 1064, would be much faster. The thing with quantum computing is that we could take this and not just go into a decimal system, but go into a hexadecimal system, or a 16-digit system, or a 32-digit system, or a 64-digit system. We could have it be where there are discrete markers. At this point, we don't even have like letters that go to 64. You'd have the difference between capital letters and lowercase letters, and those would all show up as a part of the numerical library. And if we had that, if we had 64 letters, it means this is 1064 is like what? You have, so 64 is equal to 64 to the first. What's 64 squared? It should be like 36,000 something. No, 3,600. Okay, what does that mean? That means, quite frankly, you can represent this in 2 digits. Which means now it is about 6 times faster than doing it in a binary system.
Why do you still not run into that level?
Oh, you still do. But the thing is that now just because we can transmit more data in 1 single digit, that's what makes quantum computing faster. There is a finite limit to this. Because if, assuming that you could transmit infinite numbers in one digit, this is still transmitting 1064, you can make it 11 times faster than what it's at. And then there's no way to make it faster using quantum computing. So, yes, it does increase the speed. Yes, it is factors faster, but there again is a finite limit to it. This continues to be the overarching limit that prevents us from going any faster. Great question, though. Any other questions? Okay. You have a reading assignment due Monday. That's it. I'm not giving you any more quizzes in this class. If I gave you a Pro Micro, please bring it on Monday so that we can start working on programming.